helping me to do my job and to create what I'm going to present. So first of all, I want to say thank you to all my friends and colleagues from Milano. They are a lot. They are funny guys, and a group of people doing and applying different techniques, from bulk petrography to geochronology and statistics. So I'm very lucky to have these people working with me, and led by Eduardo Garzanti in this group that we call a group of provenance studies. But I have also to say thank you to all the people from the IODP expedition 355 and some friends of mine that during my life helped me to keep going and to do my studies. So I want just to introduce you a short list of what I'm going to present. The idea is to introduce a little bit what does it mean to do provenance studies, and what we do in Milano is to apply bulk petrography in heavy minerals. I will also explain you why silt is so important in this type of studies, and in the case history related to the turbidites and the sedimentary archives stored in the Indus and the Bengal fan. To do this, I would like also to introduce you first to the laboratory for heavy mineral separation, and after that we have a good heavy mineral separation, we can do a proper identification. And in the recent years, I started to couple classical optical methods by microscope with Raman spectroscopy. I will give you some insight about these techniques. After that, we build up this knowledge and this language. We try to apply this in a natural laboratory. And the best laboratory I can imagine is the Himalaya, and in this case, the Western Himalayan, the Indus catchment, and the turbidites in the deep ocean in the deep Arabian Sea. So basically, I will show you what we know, what is already done about the composition of the sources on land, so the source of the detritus. And after, we try to see how this signature is transferred first in the foreland and after in the deep ocean. In these last years, now it's 7 years after our expedition 355, a lot of paper have been published using different proxies. I will just give you some comments about how the use of different proxies is fundamental for such complex study. And after, of course, because this is not the end, but the beginning of the story, what's next? So we apply sedimentary petrography, and in particular, I love to apply one of the methods that are in the proxy that are used in this world. And heavy minerals is analysis. It's a proxy that can be used in modern settings to reconstruct the composition of sediments and to couple this, to link this with the source rocks. After that, you recognize the source rocks, you can try to recognize the source area where these rocks are eroded and exposed. Of course, these techniques was developed in the 1970s, first for the industry, for the hydrocarbon industry. And I have to say that I want to mention Maria Manga, because most of the progress we've done is thanks to the work of this outstanding researcher. I want to define heavy minerals for people that are not used with these methods. There are minerals with a density greater than 2.9 grams per cubic centimeters. And you can see in these photos a range of shapes and colors and density. The density, of course, is fundamental in heavy minerals because heavy mineral depends on the source rock, but they can be concentrated for hydraulic sorting, and they can be destroyed by selective weathering. Superficial weathering can be very important in equatorial zone, for example, and diagenesis, so the dissolution after burial, it's also important going back in time. And we will see the effect of this bias trying to use this proxy for provenance studies. I anticipated you the importance of silt, and I discovered this is a place in USA. It's a small village in somewhere in this country, in this big country. Traditionally, if you check the literature for provenance studies, you will find a lot of paper dealing on sand, because sand for tradition is the grain size used for bulk petrography. And in the past, in particular, thanks to Maria Mange, traditionally the 63 to 150 micron grain size, so fine and very fine sand, was the grain size window analyzed. Heavy mineral concentrate in the finest tail of sediments. And so I started to have a look in the coarse silt down to 32 micron. But after starting my expedition and working in very fine sediments, like in turbidites, when you are far from the source, I started to create a protocol to study silt. And the reason is because the silt is really important, because if we want to reconstruct the source of sediments, we cannot ignore this grain size. You can see an example here about the Bengal Sea, and the silt in superficial suspended load of big river like the Ganga, Brahmaputra is up to 90%. But also in the deep, it's up to 40%. So if we try to reconstruct the provenance of sediments ignoring silt fraction, we can introduce a bias and do big mistakes. And sometimes silt is the only available grain size. So this is why I spent some time to create a protocol for physical separation and identification of grain. And of course, the optical methods by microscope was not enough. This is the reason why we started to introduce Raman spectroscopy. But first, when you have a CT sample, you need to prepare it. And I can tell you, it's a muddy work. I mean, it takes time, and we create a special sieves that are made in nylon, so you can use only one time, and they work very well. The result is that now we can work down to 5 micron. And the reason we can do this is because we developed a protocol to separate this grain size in different depositional environments, in suspended load, in the lowest deposit, in turbidites. So now we have an experience. So it's a job that you learn now in 1 week, but it took years to prepare this protocol. So in the end, you have a very clean heavy fraction and the light fraction on the other side. You can see in these photos the procedure from the sieving to the partial freezing method of the heavy mineral separated in the centrifuge. And here, after the recovery, we weigh the amount of heavy mineral, and this is a very important point. And this is very important, the amount of heavy mineral, that we wrote a paper with Eduardo Garzanti in 2007 explaining the importance of the heavy mineral concentration index. I can show you this in details later, but consider that this number, that roughly is the concentration of heavy mineral in the grain size we analyze, is related to the source rocks and to the structural level in erosion. Here, for example, you see a table from a paper from this work where we had the Himalaya from the batholiths to the amphibolite facies and going up in the structural level to green schist facies and very low-grade meta sediments. And you can see that the concentration of heavy minerals starts from 25% and move to 10, 8, and in the sedimentary cover, we have only 1% of heavy mineral. So you can understand that a simple number that you get in the lab, just weighting the amount of heavy mineral, it's a first important point to consider for the rest of our discussion. So, how identify minerals? This is a point. Normally we use the microscope, but when you want to work in silt, optical properties helps a lot, but sometimes they are not enough. So the experience of the operator is important, and sometimes because the grains are too small or because you find strange rare minerals, it's not so easy in the silt fraction to recognize properly each single grain. And this is the reason, because sometimes minerals, they have the same shape, the same color, but they are completely different. Here you see a tourmaline and an amphibole, a calcic amphibole, an ornament. They look similar at first sight, but they are not. So the message to take home is take care about the shape. Doesn't help. You need to look at so many optical properties. And this is the reason why we started to introduce a new additional tool, Raman spectroscopy. These techniques can be applied directly on single grains down to few micron. And you can see from these slides that you can recognize properly each single grain. In particular, here you see two examples for a zircon. What you get is a spectrum with the intensity and a Raman shift, a position. And this position of the peaks is characteristic and depends on the chemistry and the crystal structure of your mineral. So, for example, here we can recognize a crystalline colorless zircon from a metamitic zircon because they are similar, but the metamitic one shows a shift of the first peak you see here toward the lower frequency. So we have also additional quantitative information. We have applied this in this year, and we are doing this also now on different group of heavy minerals. Here you see you can apply this for calcic amphibole and sodic amphibole. And in particular, looking in the high frequency region, for example, when you look at the pleochroism of the amphibole, you can quantify the amount and the ratio between iron and titanium that is responsible for the color and the pleochroism of these minerals. So, for example, you can distinguish magmatic from metamorphic amphibole that is quite important in sediments. We have done also this for other calcic amphibole in the tremolite ferroactinolite series. And we are now waiting for the submission of a paper we have done about orthopyroxene. This can be applied also in clinopyroxene, in aluminosilicates, in meta-sedimentary heavy minerals. So it means that these techniques can be applied in all the triton minerals you can find in real sample. Here you see the group of the epidos that is quite big and complicated. We can distinguish, looking optical properties, different varieties and different minerals. But to go deep in detail, to do something quantitative, we are preparing with Mara Limonta a paper now about this technique, how to distinguish clinozoisite and epidote, that are two proxy very important for the metamorphism in orogenic settings like the Himalaya. The garnet, of course, also can be identified, and this is an example of what we can do. So now that we know how to separate heavy minerals and how to recognize heavy mineral, we try to apply this in a case history. And this is the place where we did our expedition in the Lakshmi Basin. And you see we are close to the Indian passing margin, and we have the Indus here, and the Canyon and the Fan. And here, of course, we have the Deccan Traps and two big rivers, the Narmada, the Tapti, draining these rocks. So we have to consider this. To do this properly, the best is to look at what is already done in literature, starting from the geology. And this is not an exhaustive list, and I apologize for all the missed references that are not here, but just dealing and speaking about the composition of sediments, bulk petrography, and heavy mineral, I want to cite these papers first. And I want to show you in details what we know about the sources, because our aim is, after that we know each domain in our Western Himalaya, which type of source rocks and which type of heavy minerals can provide to the system, we want to see if we are able to recognize this composition, this suite of heavy minerals and this suite of rock fragments in the deep ocean, in our turbidites. This is a challenging work, I have to tell you, because of course, when we work on single end member, when we have small rivers, like the rivers indicated in this figure, draining single tectonic units, we can recognize the signature of each domain. But after, when we have to consider the big rivers like the Indus, of course, the mixing of these rocks in different proportion and is fundamental. Hydraulic sorting is fundamental. The grain size we consider is also important, and the time and the fact of time and the genesis is also important. So we have to say that this is challenging when you do this work in the modern, and became more challenging going back in time. In any case, we start, and just to show you the complexity of the system, if we simplify the sources in the Asian margin units and in the Indian margin units, starting from the Asian margin units, if we look first at the Karakorum belt, we can consider the Karakorum like the North Karakorum belt here, and after you see the batholiths of the Karakorum, and the southern part, the metamorphic part, indicated here with this orange color. You see there are numbers here, number 5, 6, 7, and 8. There are rivers draining these units, the Unza, the Hispar, the Bralgo, the Ushchek. We have studied the sediments carried by each single river. These papers, of course, it's a long work. It's a collaboration with other co-authors. And in this case, this work was done by Eduardo Garzanti, by Liang, by other co-authors, a long list of co-authors. This is why I told you in the beginning, this is a work that you can do only if you have a team of people working together. So about the Karakorum, we can consider the bulk petrography. And for example, the northern part, where we have an important sedimentary component, is a feldspatho-quartzolithic composition with abundant carbonates that we recognize in detritus. Moving in the central part, the batholith of the Karakorum, we have more feldspar-rich quartzoso-feldspathic composition. And in the hand, moving to the south, the southern Karakorum metamorphic belt, we have a lithofeldspato-quartzose composition with also marble grains of higher rank, metamorphic rank. What about heavy minerals? In this sedimentary part, in the northern part, we have not so many heavy minerals, and we have basically some characteristic heavy minerals like epidote, chloritoid. Sometimes we have some andalusite from contact metamorphism. We typically carbonaceous materials as inclusion. In the central Karakoram, for example, we have mainly amphibole, because this is the main heavy mineral you find, with a little bit of titanite, epidote, allanite, for example, and this is the composition. When we move in the metamorphic part, in the metamorphic belt, we start to see staurolite, kyanite, and sillimanite bearing metasedimentary rocks, and we can have also some diopside that is related to the dolomitic marbles. So we have some characteristic minerals that we can use as a proxy. If we move now to the Trans-Himalayan arcs, and here we have the Koistan and the Ladakh, studying in detail the composition, for example, related to the heavy minerals, here we see that the Koistan is very important in terms of concentration of heavy mineral. You can see that it provides from 30 up to 44% of heavy mineral. So this river, the 1, 2, 3, and 4, so from the Swat, the Kandia, for example, the Gilgit, are river draining the Koistan, and they carry specific heavy minerals so that we can use really as a tracer. For example, they have a lot of orthopyroxene, rich in iron, hypostine. They have garnet. They have also amphibole, clinopyroxene, and also zoisite that we can find in different units that are characteristic of the Koistan arc from south to north. In the Ladakh batholith, you see the concentration of heavy minerals is lower, but it's quite abundant, 10 to 13. And amphibole, again, calcic amphibole is the dominant transparent heavy mineral. We have again a little bit of titanite, clinopyroxene, epidote, and garnet is very rare. So now we can move to the Indian margin units, just to have an idea. And for example, here you can see that we have already studied in details the concentration of heavy minerals, the bulk petrography in each river draining these units. So we have a quantitative idea of the ingredients that we have in the system. Just to give you some example, the Tethys Himalaya, for example, provide not so many heavy minerals because we have metasediments basically. So we have only 1% of heavy minerals. In these heavy minerals, we have a lot of ultra stable heavy mineral like zircon, tourmaline, but it's only 1% of the sediment. So we have a lot, up to 50% of zircon, tourmaline, and rutile, but it's the 50% of the 1%. And we have to consider the fertility of each domain in respect to each mineral if we want to use this knowledge after to reconstruct the budget. In the Greater Himalaya, for example, the concentration of a mineral is higher, it's up to 10%. And in this case, for example, we can find only little amount of ultra-stable minerals, and we have a lot of amphibole, garnet, and epidote. But we have also specific high-grade metamorphic minerals like sillimanite, for example, and kyanite. So these are specific. After we have relatively little outcrops like in the Nanga Parbat, where the heavy mineral concentration is up to 18%, they display a very rich transparent heavy mineral suite. And the Astor River that is draining these rocks is dominated by calcic amphibole, blue green hornblende, with epidote and subordinate garnet and clinopyroxene. What about Lesser Himalaya, for example? Lesser Himalaya, again, because we have this basement that are in different phases of metamorphism. When we have very low-grade metamorphism and metasediments, like in the outer Lesser Himalaya, the amount of mineral is very low. It's around 1%. When we move to the green schist facies in the inner Lesser Himalaya, we jump up to 7% of heavy minerals, 6-7%. So you see that the amount of heavy mineral is really important because it's directly correlated to the different metamorphic facies of the metasediments we are investigating. So starting from this knowledge, we try to have a look to the rock fragment. And we can do, again, this thanks to Eduardo Garzanti, that he published this nice review. And now here we see the end member, the orogenic signature in the Indus catchment. You see here, this is the first in the top, is the North Karakoram. And you can see feldspar, quartz, and the carbonatic lithic fragment that are quite abundant. On the right, you see the South Karakoram. And you can see clearly, I'm not a specialist of bulk petrography. My friends probably they are smiling because basically I don't look in section. But in any case, you can see here quartz and plagioclase, and you can see the high grade of these rocks because you see biotite here. And the same, we can look at the Ladakh arc and we can compare with the Koistan. And in the Koistan, we see, for example, in this photo, a lithofeldspato quartzose plutonoclastic suite. And this is very rich, this composition is very, very, very rich, for example, of hornblende, but we have also a lot of, you see, of amphibole here, but we have a lot also of epidote in this case. So we can use this knowledge. We have the Nanga Parbat here, and for example, we have a very specific signature from the Waziristan ophiolite. You can see these beautiful ultramafic grains in this suite. So it means that really, when we look at the petrography, we have the bulk composition and we can distinguish different domains. When we have end member, the problem starts when these end members start to mix, and this is more challenging, as I told you. And we can do the same for the heavy minerals. You see the heavy minerals, this is a table of number, but you have the Karakoram, and you see the concentration, it's quite stable, the Ladakh, the Koistan, the Greater Himalaya, the Nanga Parbat, and for each of these samples, we have the amount of zircon, tourmaline, rutile, titanite, apatite, amphibole, pyroxene, olivine, and zoisite, and the other high-grade metamorphic epidote, garnet, and high-grade metamorphic mineral. So we have the control on the modern end members about the composition with all the variability that is in the real deposition and environment, but we have this knowledge. So we can try to use this. So now the point, we start to mix this material and we see the composition of the big rivers in the orogenic provenance. Orogenic provenance, it means in terms of heavy minerals, hornblende, epidote, and garnets. And you can see, if we consider 12 samples about the Indus River, an average composition that is basically identical to the Brahmaputra River on the other side of the Orogen. Hornblende, epidote, and garnets. If we look at the southern tributaries, the Punjab rivers and the Ganga River on the other side, again, they display a similar composition. In this case, garnet is more abundant, you see, and amphibole is not so abundant, and this is strictly related to the source area and the fact that in the southern part we have a lot of high-grade metamorphic rocks providing garnet and sillimanite, for example. And we have a lot of amphibolitic rocks drained for the higher part of the catchment of both the Indus and the Brahmaputra. So this is also the amount of heavy mineral. Look, 11% for the Indus, 12% for the Brahmaputra, 4% for the Ganga and the other tributaries. So really a peculiar composition. This is what we put in the system entering the ocean. And this is what we have done, because we are like kids. We like to play with sand, with the microscope, but we need also more expensive toys, like an expedition in the Arabian Sea. I was very lucky, thanks to Peter Clift, all the people on board of the expedition, that they asked me to be on board, to work, to see and to see the core, and to do me as ride. I did a lot, and I enjoyed. I really love to do this. And starting from this work on the vessel, that it was very important. It was more important to work with other colleagues, to learn from them other techniques. We started to analyze these on board and after the expedition. But of course, you understand that the work is long to prepare this sample. So most of the work was done after in the laboratory at home. And so what I did is first a publication with Sofia Bratenkov and Annette Ann and other co-authors and Peter Clift. And what we did the first is, of course, after that we recovered this core. I want to show you just some photo. And I wish that all the young people attending this meeting in their life, they can join one of these expeditions. It's really amazing, and it's something that will change your career and your life. So really, I was so happy to do this expedition. And here you see people working, the very important people that they do their hard job recovering the core, and our colleagues. Here you see Stefan and Annette and Sofia and other friends that are looking at the core. And here you can recognize another friend that is attending today. And this was the last core on deck. Everyone that was on board remember this sound of core on deck when they call for it. So this is the aspect of our core. On the left, you can see this homogeneous core. This is interpreted as a channel fill, and these on the right are interpreted as overbank deposits. You can see that basically it's a fine sand or mixed with silt and clay. And what we have done in this first work is focusing in this unit 2 that is located in the Pliocene and Pleistocene. It was more a sedimentary paper to look at the mineralogy, to distinguish different deposition and environments, and of course to check the composition. So basically what we have done is by microscope, applying both the microscope and Raman spectroscopy, to look at the suite of heavy mineral and their concentration, both in overbank deposit, where suspension is the process that dominated the process with silt, and in channel fill, where tractional currents dominate these deposits. You can see the amount of heavy mineral, typically higher where tractive currents are more intense, up to 6%, and lower, half, 3%, in where suspension sorting is working. And typically you see the grain size smaller, about heavy minerals. And in the suspended material, you have a lot of platy minerals that are concentrated by suspension sorting. About the composition, this is a sample in the Pleistocene, this is a sample in the late Pliocene. And you can see that we have amphibole, hornblende actinolite, we have epidotes, we have garnet. So we have the orogenic signature. This is typically the same signature we find in the modern Indus River. And we have some interesting mineral like kyanite, that is a polymorph of aluminum silicates related to high pressure rocks. So definitely it comes from the sutured zone, from the high pressure rocks in the orogen. And we have other heavy minerals that we can consider. We have done this in details, in a quantitative way. We have no time to go deep in details. If you are interested, you can have a look at the paper. But the message to take home is that we can, if we compare the Pleistocene, the Pliocene, and all the sample in our core for this interval of time, we have a very homogeneous composition. So the main composition in terms of amphibole, epidote, and garnets, and accessory minerals, it doesn't change through time. This is the first point. And also, if we look at the bulk petrography, it doesn't change in this interval. So what I've done, like an experiment, this is intriguing, is also to look in details at the chemistry of single minerals. For example, you can see here 3 samples, the modern Indus, and a sample in the Pleistocene and a sample in the Pliocene. On the left, you see the heavy mineral suite, and we have to recognize that it's identical through time, from the Pliocene to the modern. On the right side, if we look at just this red part that is related to garnet, if we look at the garnet, we see differences, for example, that before was not possible to recognize. The first sample is identical to the Pleistocene one. So the modern Indus related to the garnet composition is identical in varieties like the Pleistocene one. But we see a sharp difference in the composition of garnet in the Pliocene. So what does it mean to me, this? That if we look at the bulk petrography, the heavy mineral, and we start also to look other proxy in details, we have a chance to link this composition to a specific source rocks. What we know about the composition of garnet, for example, in the source area? Again, thanks to other work, Liang et al. In 2019, he worked on the same river that I showed you before, reconstructing the composition of the garnets in different domains. I have to say that already Alizai, before him, have already done a similar work in the past that fits very well with what Liang et al. Found in this paper. But it's intriguing that if we consider the same variety, this one, the pink, that increase in the Pliocene, this variety, the pink, is the C1. The C1 is a variety of garnet that start to have more magnesium, so it means more high-grade metamorphic rocks with a little bit of calcium. So it could be both amphibolitic facies or also sometimes related to high-grade metamorphic rocks like eclogitic facies. What does it mean? If we look in the possible sources, but this is just one sample, just an example, you can see that in this work, the C1 is typical of these 2 sources, one in Koistan and one related here to the Himalaya. So the problem is now that we cannot give an answer to be sure about something just looking one proxy. But you understand that if we start to use different proxy, we can do probably something meaningful. So what we have done is also to add a new sample to consider the entire core. And we did the bulk petrography where we have sand and heavy minerals where we have silt. And I want to show you our result. Starting from the bottom, the oldest sample we found are Paleocene mud rocks in the Lakshmi Basin, dated by Claire in the Routledge in the age model. Basically just before the collision that is dated around 60. So here we have something that is in the Indian margin. And we see, in terms of bulk petrography, basically a yellow clasticite completely weathered. But in this mud, we were able to recover a few heavy minerals. You see, minus the 0.01%. And what they are? Needle of apatite, beautiful evidral crystal of aegirine, volcanic glass. And we were able to link this to the late volcanic activity related to the Deccan Troughs. There is a volcano that in this area provided this aegirine, these very specific minerals. So this is amazing. From this mud, we were able to get this information. So going up, the lowest basal turbidites we found were dated up in the Miocene 50 million years, around 50 million years. And here we recognize orogenic minerals. So we have hornblende, we have epidote, we have titanite, and the amount of the mineral is up to 2–3%. So also the bulk petrography tells us that this is, in this moment, a provenance from a Paleoindus river. So this is from the Himalaya. We found something unexpected during our expedition, a mass transport complex, a slide that unfortunately destroyed our stratigraphic record. But it's interesting to see what we found in the heavy minerals. In this, that basically is a breccia, a wakestone with foraminifera. And we found a few heavy minerals, minus the 0.1%. And typically we found brown augite and apatite, volcanic apatite, so minerals that are related again to the Indian margin in this case. And this is because this is the provenance of the material of this slide. Now we get into the Pleistocene turbidites in the upper Miocene to lower Pleistocene. And here we find beautiful heavy minerals that now we know that are from the Himalaya. And also the bulk petrography tells us that both in overbank turbidites and in the channel filling, we have Himalayan materials. And you see the amount of mineral is increasing up to 8%. In the top of the sequence, here we have this middle Pleistocene ooze rich in planktonic forams, but also here I was able to find heavy minerals. And you see here a typical signature from the Deccan, from what we found today in the Narmada and the Tapti. The augite, that is the clinoperoxene dominated in this type of sediments, a little bit of pyroxene, some sodic amphibo, and some like a glaucophan. In this case, we have to consider also that the Ghat range has metamorphic rocks in the Indian margin. So we can have also metamorphic minerals, a little amount, also derived from the basement eroded that is in the Indian margin. So basically, putting all together, this is the image of this second work that we did to reconstruct the provenance of the sediments from the bottom to the top of the fan. And we see the differences, both in bulk petrography and heavy minerals. Recently, I have to say, I was really intrigued by the publication of a paper by Zhu et al. About zircon uranium lead age constraints on the truly same sample I have analyzed with heavy minerals. I tried to compare the conclusion in this paper with what I found looking about petrography, but specifically heavy minerals. And I have to say that in this paper is well explained and everything is justified and the arguments are provided in a proper way. I have to say, a very nice paper. What I just say you is that where they found differences, changes, for example, they see from the blue, these are their sample, and to the red that you see here, a change, for example, in the contribution of material derived from Karakorum that decrease from 17% to 35%. And so basically moving up to the top and increasing in the Himalayan erosion respect to the Karakorum. If I look at the heavy minerals, I see no these big differences. If I look at the bulk petrography, I don't see these differences. So this is important because it means that we have to consider different proxies. So what I like to say is that no one approach is right and another is wrong. But it's really important to apply different proxy in a holistic way to approach a so complex case history. So my message is basically that this is not the end of the story, because there are things that are not completely demonstrated. And I think that in the natural sedimentary archive, there are a lot of information stored that are still waiting to be squeezed out and to be investigated by next future researchers that are listening in this talk probably. So in conclusion, I think that from the methodological point of view, Raman spectroscopy is the right techniques to be coupled with optical studies to investigate sieve-sized sediments. And in turbidites, it's the right techniques. We demonstrate this. On the other side, from geological results, in this context, so complex, we have seen differences in the end members that became more difficult to be recognized when you have a big river and the mixing. If we want to extract not only the source area and the source rocks, but also we want to integrate this with other proxy to investigate the climate of the past, we need to explore more in detail, I think, with varietal study, the most important minerals, the amphibole group, the epidol group, and the garnet group that are present in big amount, more than zircon, for example, in all sources. So we can differentiate at this point the Himalayan versus the Indian peninsular sources, but what we need is to go deeper in detail. So also, I wish, because I've seen Peter is here, Christian is here, and a lot of people involved in this. After 7 years passed since the last IODP expedition, if we are happy and we try to collaborate, it's also time to compare different fan, the Indus, the Bengal, and the Nicobar fan, to see this big origin in the entire frame that it needs. So thank you very much for your attention, and thank you really for this opportunity to share with you our studies. Thank you.
Thank you very much, Sergio. Thank you very much. One comment that I would like to put out there is this: your presentation should be used by IODP as a justification to keep the archive happy for a very long time for newer generations. If you have questions from the audience, please put them in the chat or raise your hands, and let's ask Sergio. Until people are thinking, I would like to ask a question or make a comment that I was really impressed by the fact that Indus and Brahmaputra are so similar, and everything that comes from the Himalaya are so similar. It's a clear fingerprint for the two sources. That is probably would provide the unifying framework between the fans.
Yeah, this is a good news because it means that the sedimentary archive, it preserves the original signature. So it means that the agenesis is not so intense to destroy the pristine suite of heavy mineral and rock fragments. On the other side, I don't want to oversimplify, because we have seen in the paper of Zhu et al. That it's possible to differentiate different sources. I want to be very careful about the amount of the mineral we consider, because if we see a peak from a specific source for a mineral, like for an age of a zircon, that it represents only 1% of the sediments, we have to consider this in the budget. It's not only because we see this age, it's also the amount of this mineral we have in the sediments that we have to consider. This is why I think it's very important, it's fundamental, because it can suggest and can underline some new idea, but after it's better to observe also varieties of common heavy minerals. We have seen with the Mara Limonta that we are working a potential in the epidote composition, for example, through time from different sources to differentiate green schist facies and the passage to amphibolytic facies, and also to recognize high pressure varieties. And the same for garnets. Garnet is extremely sensible to the source rocks. So my dream is to go deep in detail, analyzing these single grain varieties in the same sample. Now that I've seen these nice new papers, to see how different proxy can tell little pieces of the same story, because this is the problem. The story is one, but we see different information from different proxy, and sometimes they are not synchronous. We see something that with the proxy that is completely absent in another. So this is why it's important to have a complex story.
We have a question from Peter.
Yeah, Sergio, well, a question and a comment. So I think that what you're doing is very important, especially because of the problem of distinguishing these different Himalayan units using zircon only, but we just can't do it, can we? We don't know the difference between the Tethyan and the greater and even the outer Lesser Himalaya. So I think the combination is really powerful, what you're doing. My question is, when you take a sample from the rivers to try and characterize the source terrain, like the Gilgit River, or how do you know that that's representative? Are you worried about hydrodynamic sorting, that you're not really getting a good average? How do you account for that?
This is a fundamental question, Peter. This is a matter of another presentation. I apologize I didn't explain deep in details, but after that I introduced the meaning of provenance studies. The first point is the sampling. We have dedicated a lot of attention and papers through time about sampling. And you are right, when you are in the field, you are in a rush, you have to collect the more samples you can, there are logistic conditions, you need a representative sample. The best you can do is to avoid big mistakes, like to collect a placer or to collect something that at first sight, it looks not representative. But what is it representative? We have instruments, quantitative instruments, to quantify if our sample is a good sample in terms of representativity. I mean, I can compare the amount of heavy mineral, the concentration of heavy mineral with average sample. Now we have hundreds of samples. So I can compare, I can see if in other sample in the same catchment, I find always the same concentration or not. This is a way. I can compare with the geochemistry. I can standardize my analysis to an average composition to see if my sample is enriched or depleted in some elements, to tell me if it is representative or not. In the end, we have checked this through time, not in particular in the Alps, collected samples in different years in the same place, and basically, it's true, you can find some differences related to grain size, for example. But if you control the grain size, if you control the geochemistry, if you control the concentration of heavy minerals, you have under control that it is representative. And trust me, Peter, you can do big mistake also after, when you are in the lab, when you take it up a little spoon of your sample without taking care about what you are doing. So it's not only in the field, the problem, it's also in the lab, in the window, the grain size window where we consider that has to be as wide as we can, just to avoid to miss the tail and some minerals that is essential. This is what I mean. But we have tools to control that it is representative. You cannot do the work of a river. I mean, thousands of geologists can do in the Indus catchment collecting rocks, but never they can do better than a river giving you an average composition of the catchment. So basically, geology works better than us.
Thank you.
More questions, please?
Probably scared about heavy minerals. Nobody wants to do it after this presentation.
It's a lot of work.
Yeah, I remember a guy that in London told me, but this is time consuming. And I say, I love time consuming stuff. And so, yes, it's time consuming.
Can you do it? Can you do it from satellite?
Oh no! Now you want to destroy my work, but probably not from satellite, but from a drone we can do something probably in the next future. I'm not joking. It's possible.
Satellite.
Yeah, no, I have colleagues that honestly they've already done something about this. It's a different scale. It's a matter of scale. But of course, you can get and you can reach bigger areas. And so, for example, I've seen a nice paper dealing on the composition of sand dunes observed by the photographs. And if you have a chance to also do a check with the real sample in the field, not only from the satellite, so you have to compare the photo with the real sample. It works very well.
Based on visual properties.
Yeah, it's probably, it will be possible to do something in the future. They've already done.
Well, thank you, Sergio. Please, if you have more questions, get your courage up. Last few minutes. Thank you, Sergio, very much. I would like to announce that next on February 2nd, next talk, it's going to be about more about oceanography and ecology, the influence on the monsoon on marine ecosystems, and the speaker would be Kenji Matsuzaki. Apologies, and that's going to be on Schedule B. Thank you, Sergio. Thank you, everybody, for participating.
Thank you very much.
Thank you, Sergio. Bye-bye.
Bye.
Ciao. See you.
Thank you. Bye.
Ciao.